In this video, we'll have a look at the linear algebra exam of January 2023. Well, the exam has the same format as in the previous year. So there is a first question about the 4 fundamental subspaces of a matrix. The second question deals with a system of equations that you have to solve. And this system of equation depends on unknown variables, so that you have to discuss. The third question is about a least squares problem that you have to solve with the QR decomposition. And finally, you have to factorize a matrix A that is positive definite in 2 ways, one related to the pivots and one related to the eigenvalues. Without further delay, let us start with the first question. Here you have to find the basis and dimensions of all fundamental subspaces of the matrix A that is shown. You have to compute the rank of this matrix and then express the 4th column of the matrix in terms of the other columns. As usual, try to solve this exercise by yourself and look at the solution afterwards. So the first thing that we do is to use this augmented system. You see that you have the matrix A, and then next to it, well, you put an identity matrix of dimension 4. And what we'll do first is to bring it in echelon form. As you can see here, it's in echelon form, and then we'll bring it in row reduced echelon form. So that means that we create zeros below the pivots first, and then in the end we also create zeros above the pivots. So here we have our first pivot, right? And we have all elements that are 0 except this one. So what we'll do is use this elementary operation. So this means really that we take this row over here and we subtract this row times 1, right? The multiplier is the element that you want to eliminate divided by the pivot. So if you do this elementary row operation, this is what you obtain. We have our next pivot over here. Below we have one element that is non-zero, so we'll use this elementary operation to make this element 0, and then we'll multiply by -1 so that we end up with a pivot that is 1, right? So this is what we end up with. And here you can see that we have our third pivot over here, and to create a 0 below, we subtract this row here from this row over here. So the multiplier is the element to eliminate divided by the pivot, right? And then we create this augmented matrix over here, and we see here that we have a row of 0. So we only have 3 pivots, so we know that the rank of A is equal to 3, right? So now we have our system here in echelon form, and to bring it in row reduced echelon form, we have to make this one 0, and you can do this using this elementary row operation. And this brings the augmented system here in row reduced echelon form. So let us continue with the column space. We know that the rank of the matrix is 3, so the dimension of the column space is 3 as well. So we see here that the 3 first columns are independent, but since we're looking at the column space of A, we have to go back to the original matrix, and we take the first 3 columns and we take, well, linear combinations of these columns, and this generates the column space. Remember that you cannot take the columns of the row reduced echelon form, because when you do row operations, of course the column space is modified. Okay, so this gives us the column space. We know that the row space, which is also the column space of A transpose, is also of dimension 3. There you can take, well, the rows of the original matrix, right? Or you can take the rows of the R matrix, the row reduced echelon form. And again, you have to take linear combinations. This is what you see over here. Here we have taken linear combinations of the original rows of A, and here we have taken linear combinations of the first 3 rows of R. But of course this is equivalent. We have seen that the first 3 columns of A are independent, but you can see that the 4th column is depending on the first 3 columns, and you can see the linear combination from the coefficients that you see over here. So C4 is 1 times C1 minus 1 times C2 plus 1 times C3. This is written over here, and you can check this, right? This is C4, C1, C2, C3, and here the coefficients 1, minus 1, and 1. And if you add this up, you will see that this is indeed correct. Let us now have a look at the null space of A. Well, here we have the matrix R, okay, and R, you can write it as an identity matrix of dimension R, F, and then you have zeros here and zeros here, right? And the null space of A is spanned by the columns of N, and N is constructed as follows. It's minus F, and below you put an identity matrix of dimension N minus R, right? And N is 4 here, it's the number of columns, and R is 3, right? This is the rank of the matrix. So if you take F over here, here you have it, you put a minus in front, and you'll have, well, the 3 first elements here, and here this identity matrix of dimension N minus R, well, N minus R is 1, so it's a scalar, and this is what you obtain, right? So this is the null space of A, and you can check that A times this vector should produce you the 0 vector. So the null space is obtained by taking linear combinations of the columns of N, but there's only 1 column. So this is what you obtain over here. So we're left with the left null space of A, which is also the null space of A transpose. Well, you can obtain it by looking at what you see over here. If you take this row vector and you pre-multiply A, what you'll have is a 0 vector. So if you look at the null space of A transpose, well, you'll have to take this vector over here and transpose it, right? And any combination, linear combination, since it's only 1 vector, so the vector multiplied by any delta here will produce the left null space. There are of course a few elementary checks that we should do. We know that the dimension of the column space plus the dimension of the left null space should be m, which is equal to the number of rows, right? The number of rows is 4, and you can see that this is indeed correct since we have 3 basis vector for the column space and 1 basis vector for the left null space. Similarly, the dimension of the row space plus the dimension of the null space should be equal to the number of columns n, and this is also 4. And we see that we have indeed, well, 3 basis vector for the row space and 1 basis vector for the null space. So this property is valid as well. Well, the next things that we should check are the orthogonality properties. We know that the column space is orthogonal to the left null space. This means that every vector in the column space is orthogonal to every vector in the left null space. And this is of course the case for, well, the basis vectors. So this means that this vector is orthogonal to this one orthogonal to this one, and this one orthogonal to this one. And of course you can check this to be true. Similarly, you have that the row space is orthogonal to the null space, right? And this is again true for every vector in the row space and every vector in the null space, in particular for the basis vector. So this vector here is orthogonal to this one is orthogonal to this one, and this one is orthogonal to this one. You can also use these vectors over here. And of course you should check this, and if you do, you will see that this is the case for the solution that we have found. And this concludes the first exercise. Let us now have a look at question 2. Well, we consider a system of equations that depends on two values a and b, and you have to find the values for which this system of equation has no solutions, an infinite number of solutions, or a unique solution. In the cases where you have an infinite number of solutions, you have to express the solution in full detail. As usual, push the pause button and try to do this exercise by yourself. Well, let us have a look at the solution. What we do is stack the matrix A right next to the vector B, and then you can start row operations, elementary row operations. The first thing that you have to do is to bring the matrix A in its upper triangular form. So you have to produce a echelon form of the matrix, right? So here we have our first pivot. Here are the two first elementary row operations to produce zeros here below. Remember that the multiplier is obtained simply by taking the element that you eliminate divided by the pivot. If you do these two elementary row operations, this is what you obtain. Here is the second pivot, right? Now we want to create a zero over here. This is why you have this multiply over here, and in the end, well, you obtain the echelon form of the matrix A. And now we can start discussing. You can easily see that when A is different to -2, we have here an upper triangular matrix, and you have a unique solution that you can obtain simply by doing back substitutions. If A is equal to -2, we have a row of zeros here. And if B is different from 4, of course you have no solutions. If A is equal to -2 and B is equal to 4, then we have a 0 as well over here. And then we have an infinite number of solutions, right? So if we plug in A is equal to -2 and B is equal to 4, this is the, well, augmented system that we obtain. Now, in order to find and to express this solution in full detail, what we'll do is bring the system here in row reduced echelon form. So this means that we create a 0 above the pivot as well. We do this using this elementary row operation. If you do this elementary row operation, this is what you obtain, right? And what you have over here is F. This is what we called F in the course, and what you have over here is dr, right? So the solution is the particular solution, and well, the particular solution xp, this is really dr, right, with a number of zeros over here. Here we have the rank. The rank is 2 over here, so we have 2 elements, and here we have n minus r elements, where n is the number of columns. So in this case, it's simply 3 minus 2, 1. So this is really here the particular solution. And then we have to add, well, a linear combination of the columns of n And n you obtain simply by taking minus f, and then you put an identity matrix of dimension n minus r. N minus r in this case is 1, simply a scalar, and f is given over here. So you have minus 5, minus 3, and 1. We only have one column, so taking the linear combination is simply adding alpha times this vector over here. And this is what we called xn, right? And this gives you a full description of the case where you have an infinite number of solutions. Well, let us now have a look at question 4. We need to solve a least squares problem using the QR decomposition. We have to explain the usefulness of this QR decomposition in this particular least squares problem. So what you have to do is to fit the function that is given to 4 points that you can see on the screen. As usual, try to do the exercise by yourself and push the pause button. So if you take this equation here, you can rewrite it slightly to obtain this form over here. You have a dependence in x over here, and over here. So we consider 4 points. So we consider x is equal to 1, x is equal to 4, x is equal to 9, and x is equal to 16. So you can rewrite this equation 4 times for, well, different values of x. X is equal to 1, x is equal to 4, x is equal to 9, and x is equal to 16, right? y1 is 4, you can see it over here, y4 is 4, y9 is 20, and y16 is 32. So you obtain this vector over here. And well, this here you can rewrite it 4 times for different values of x, and you can, well, rewrite this and put this in a matrix form, right? So we arrive at the system of equations. Ax is equal to b. There are 3 unknowns here, but there are 4 equations. So this means that we have here a least squares problem. So why are we going to use the QR decomposition? And this is what we ask over here, the usefulness. Well, this is because we assume that we're going to do, well, a similar problem fitting this curve here to the same x. But the only thing that is going to change is the values of the y's. If you're in such a case where the x remain the same and the y change, well, you will always have the same ax over here, and the only thing that will change is the b. And then it's worthwhile rewriting stuff and do the QR decomposition of a, because if you have ax is equal to b, you write a as QR, you multiply by a transpose. You can then also use the transpose of this one. Remember that QR transpose is R transpose Q transpose times then A QR, and then you have an identity matrix over here. So you can rewrite it as follows, right? And now you can only consider this part over here and this part over here, right? So once you have the QR decomposition of A, you can rewrite the system of equations as follows, right? Here, as you will see in our case here, R is upper triangular, Q transpose is known, X is known, and the only thing that changes from one problem to another is B. So once you have done your QR decomposition, the only thing that you have to compute is Q transpose B, and you obtain a system of equations that is ready for back substitution because R is in its, well, upper triangular form. Well, let us have a look now at the QR decomposition of our matrix A. Well, remember that you have to keep the first column, and this is A1, and of course you have to give it a unit length. So this is what we do over here. To obtain the second vector, what we do, we take the second column of A, here it is, A2, and then we have to subtract the projection of, well, this column or this vector A2 on the previous vector A1 bar, and this is what you have to do over here. If you do the computation, this is what you obtain, and of course again, well, you have to give it a unit length. If you do so, this is what you obtain. Remember that the easiest thing that to obtain this normalization is to simply first multiply by 2, so that you have -3 -1 1 3, and then you compute the length, and of course the length, you can see that it's 9 + 1 + 1 + 9, right, square root. This explains the -3 over square root of 20. To obtain the third vector, well, you take the third column of A, here it is, and you have to subtract the projection of this third vector on the previous vectors that you had obtained, so on A2 bar and A1 bar. If you do the calculations, it's a bit more complicated, but not that much more complicated. You obtain this vector over here, and then of course what you have to do is give it a unit length, and this is how you obtain Q3, right? And Q is simply obtained by stacking Q1, Q2 and Q3 right next to each other. We know that A is equal to QR if you left multiply by Q transpose here. What you will have on this side is Q transpose Q, but Q transpose Q, since Q is orthogonal, is an identity matrix. So to compute R, what you simply have to do here is to compute Q transpose A. Here you have A, and this is indeed Q transpose. So this is Q1 transpose, Q2 transpose, and Q3 transpose. If you do the calculations, well, this is what you obtain, and of course you have to check that this is indeed a matrix that is upper triangular. So now that we have obtained R and that we have obtained Q transpose, here it is, well, we can go back to our system of equations that we had found here. Rx is equal to Q transpose B. R, these are the unknowns, Q transpose, and here we have RB. So the only thing that we have to compute is this thing over here, not that difficult. The only difficulty, if you multiply this one by this one, is that you'll have 100 divided by square root of 20, but very easily you can see that this is equivalent to 5 times the square root of 20. So now you can do this back substitution I was talking about. You can easily see here that 2C2 is 6, so C2 is equal to 3. In the next equation here, C2 is known, the only unknown is C1, so you can easily obtain C1. If you do the calculations, you will see C1 is equal to -5, and now we go to the top equation here with C1 and C2 known. It's easy to obtain C0. If you do the computations, you will see that C0 is equal to 5. And also again, remember that it's easy to redo another fitting for the same values of x, so x is equal to 1, 4, 9 and 16, if you have, well, different values of y. Let us have a look at the last question. We're given a matrix A that depends on A, B, C and D, and we have to find the values of A, B, C and D for which this matrix is positive definite. Then we're given values of A, B, C, and D, and we have to compute a factorization R transpose R, one that is related to the pivots and one that is related to the eigenvalues. So try to do this exercise by yourself and push the pause button. Well, let us first look at the first part of the question. So we have a condition on A, B, C, and D for positive definiteness of the matrix A. Obviously, A is equal to B because A has to be symmetric. And what we'll do is use the positive upper determinants that you see over here. Obviously, this upper determinant is 2, so it's positive. The next one is given over here. Its value is simply 2d minus 4. It has to be positive, so d has to be larger than 2. And then we take the determinant of the matrix A, right? Well, to compute this determinant might be interesting to do a row operation. So what we simply have done here is we have subtracted the first row from the second row, and this is why we have zeros appearing. But now it becomes very easy to compute the determinant, right? It's d minus 2, and then 2c minus a squared. D minus 2 is positive, so 2c minus a squared has to be positive as well. So c has to be larger than a squared over 2. If you take these values over here, you will see that this condition is not met. It's actually met with equality. So what we can expect is that we are at the limit, right? We'll have a so-called positive semi-definite matrix. So we'll have an eigenvalue that is 0 for this matrix for these values over here. Let us have a look now at the R transpose R factorization using pivots. We are using these values of A, B, C, and D. If you stack them in here, this is the A matrix that you obtain. So this is our first pivot. So what we have to do here is to bring this matrix in upper triangular form. We have to create zeros over here using elementary operations that you see over here. Remember that you have this to use this convention with a minus sign over here so that you can use these multipliers to construct the L matrix, right? The multiplier is simply obtained by taking the element to eliminate divided by the pivot. If you do these two row operations, this is what you will obtain. And as you can see, well, we have a second pivot over here, but we have already a 0 below. So this matrix here is in upper triangular form. And as expected, since we meet this condition here with equality here, we have a matrix that is positive semi-definite, right? So we have a 0 eigenvalue and a 0 pivot, and this is indeed what you see over here. To construct the matrix L, you start with an identity matrix and you put the multipliers at the right spots. That is the spots, well, where you have created the zeros with these multipliers. So now we have U and L. So we have an LU decomposition over here, right? But what you can then do is, since the matrix is symmetric, obtain an LD-L transpose decomposition. Here you have the pivots. And now it's very easy to obtain our R transpose R factorization. You take simply R, where you take the square roots of the pivots on the diagonal, right? And you multiply it by L transpose, right? And as you can see, very easily, if you compute R transpose R, well, you obtain exactly this decomposition over here. Let us now have a look at the R transpose R factorization but with eigenvalues. We have already seen that we have here not c larger than a squared over 2, but c is equal to a squared over 2, so the determinant is 0, right? The determinant of a. So we know that there is an eigenvalue that is 0, and this is this one over here. Here it says that L is equal to 2 makes the two lines in the determinant equal. Well, this is only true after some row operation, but you can easily see that if this is here L1, this is L2, and this is L3, you remember that in the computation of an determinant you can do a row operation. So if you replace L2 and the second line by L2 minus L1 minus L3, well, this line over here, well, you'll have lambda minus 2, right? Then you'll have this one minus this one minus this one. You have 2 minus lambda. And then you have this one minus this one. This is 0 minus this one. And you have again lambda minus 2. So this will be the new second line. And you see that for lambda is equal to 2, this line becomes 0. So lambda is equal to 2 is an eigenvalue. Now it's easy to obtain the third eigenvalue because you see that the trace of the matrix is 10, right? And the trace is the sum of the eigenvalues. So this is why the third eigenvalue has to be 8. Once we have the eigenvalues, lambda 1, lambda 2, and lambda 3, we have to find the corresponding eigenvectors v1, v2, and v3. Remember that we have to consider a minus lambda I times the identity matrix times vi, right? And I is going from 1 to 2, and this we have to set to 0. So if we take lambda 1 is equal to 1, we plug it in. This is the system of equations that we obtain. It's a bit difficult, so what we do is simply do some row operations. We have created zeros here below the pivot over here, so we obtain an equivalent system of equations. Here it's quite easy to see that v12, right, has to be 0, and that v11 and v13 have to be opposite. So we take 1 for v11 and minus 1 for v13. We have an eigenvector, and we are going to take a normalized eigenvector, so we divide by the length, which is square root of 2. You can do something very similar for the second and the third eigenvalue. Here we have this normalized second eigenvector, and here you have the normalized third eigenvector, right? And then you know that, well, you can stack these eigenvectors. Here you have q1, here you see q2, here you see q3. This is the q matrix, right? And here you have the lambda matrix, which is a diagonal matrix with on the diagonal the eigenvalue. So this is q lambda q transpose, right? And to obtain a factorization r transpose r, it's quite easy. These eigenvalues are positive, or here 0, because the matrix is positive semi-definite. So our matrix R is the product of two matrices, a diagonal matrix with on the diagonal the square root of the eigenvalues times Q transpose. By construction, if you do R transpose R, you obtain this decomposition over here. And this concludes the exam.